Hello, everybody. I'm creating this video for two reasons. The first reason is kind of a recap of the previous videos for those newcomers in programming, which I'm very happy about. And also, I want to provide a recap of what we've done yesterday in terms of getting the Swerve drive, starting the process of understanding Swerve. So what I'm doing here is we will start at the beginning with Excalibur. Okay, so the way that we've chosen to structure our code is through a paradigm, a programming technique called command-based programming. At the end of the day, what you want is you don't care about command-based programming. What you care about is I have joysticks, so I have my Xbox controllers, and at the end of the day, I want to control the motors, right? If I press the A button, I want to move the intake motor, in a certain direction so it intakes the note or the gain piece. And when I press a different button, I want it to start the wheels, to shoot the ball. Or I want, to adjust the drivetrain so it aims, or something like that. So yeah, at the end of the day, really the robot program is responsible for taking joysticks and converting those into commands that you send to the motors. However, it's like, how do you know what the A button should do? And which motor should and which motor? Oh, what is this motor used for? Oh, is this part of the shooter or the drivetrain? So what we do to build some structure into this, to give it some semblance, is we use something called command-based programming. And in command-based programming, there are three concepts. There's the concept of what's called a trigger. There's a concept called a command, i.e. command-based programming. And there's a concept of a subsystem. So if we look over here really quickly, the subsystem is responsible for, it knows about the motors that it's responsible for. So for example, the shooter mechanism is a subsystem, and it knows about the shooter motor, or if there's multiple shooting motors. The drivetrain subsystem knows about the 8 motors that are responsible for making Swerve drive possible. Okay, so if we look up here, okay, so a subsystem could be, for example, a drivetrain, or a ball shooter, or an arm, or an elevator. Each of these are different components of the robot that when you put the subsystems together, you get the robot. Okay, and then on the other hand, you have what's called so let's go back over here. So that's what a subsystem is. Now, what the trigger is it's a way of, so here's a joystick over here. But a joystick is actually a composition of a lot of different things. A joystick has buttons. It has the A button for the Xbox controller. It has an A button, a B button, an X, a Y, and then it also has 4 joysticks. Well, not 4 joysticks, but there's 2 joysticks, the left and the right joystick. But on each of those, there's a Y and an X. And then also the bumper, the triggers on the back of the joystick. Those are also joysticks or axes. Okay, so what you do is you want to create a trigger, and this trigger is bound to a certain action on the joystick. So for example, the A button, okay, or you can create a trigger for the B button, or a trigger for the bumper buttons or whatever, okay? And so now we have, you have a trigger which says when I do something with, when this button acts in a certain way, or this joystick acts in a certain way, okay? That's expressing your input. And then over here, this subsystem in motor, this is actually what the robot is, like what the robot is going to do. Okay, and in the middle, what's coordinating the inputs and the outputs together are what's known as commands. And this is why it's called command-based programming. Because you can create, there's this like translation layer. This command is a translation between a trigger and a subsystem. Okay, and commands are, and there's examples over here. A command can be what, so if you look over here, a subsystem is an arm, elevator, wrist, drivetrain. But a command is an action. What do you want to do with these subsystems? So for example, for an elevator, if the elevator is a subsystem, for example, a command can be elevator to high position. So this command is responsible. Okay, sorry about that. So a command is something that you're using the subsystem to do something. So this is actually what you care about, right? You care about the robot stowing the wrist or bringing the elevator to the high position or so something like that. Okay, so that's what a command is. So you see that, let's say elevator to high position. What you're going to want to do is you're going to say the trigger, when you press a button, the command elevator to high position should make the subsystem, the elevator move a motor. So at the end of the day, it's really the core piece is this command, and that's where our robot logic is. Okay, so now what we're going to do is we are going to, okay, so we are going to do this for ourselves. So what we're going to do is we're going to create a trigger, and let's call this trigger a button trigger, okay? And so how do we, remember the trigger is all about taking the joystick and creating a trigger out of it. So I'm going to call the drive controller joystick. And here you see we have, we can now access the different buttons or joysticks, okay? So for example, if we want to create a trigger out of the A button, we go like that, okay? If we want to access the B button, we just put B, the X and the Y, okay? So let's make it an A button. So what we've done now is we've created the trigger. And so now what a trigger does is, now what we have to do is we have to say, what about the A button? Is it when you press the button, it should do something? When you're holding the button, it should do something, or something like that. So for example, if you want to create a command that'll execute when you first press the button, you're going to do the on true. What does this on true mean? This binding schedules a command when the trigger changes from false to true. In layman's terms, right, what's actually happening is when you first press the button, you want the robot to do something, okay? So let's actually see that in action. So what I'm going to do is I'm going to do a button trigger dot on true, okay? And what we have to pass into it, remember, is the command that we want to be scheduled when we create the trigger. So for example, I created a command over here, just called print command, which, and we'll see what this is doing in a second, is when the command is initially scheduled, it's going to print out a message. Okay. So we're going to do new print command. We're going to pass in a button command triggered this. Okay. So again, what this line is saying is when the A button trigger is when the A button is pressed, we're going to print this print command. Okay. And now let me do something like this. Initialize. Okay. And now I'm going to do execute. Okay. So we're going to see what's actually run. Oh, oops. I think it's that button, yeah. So what I'm going to do is I'm going to simulate this code. And we're going to actually see it in action. So let's look over here. Continue, I think. Here. So this is the simulation, okay? And now we have to, because I don't have an actual joystick here, I think if I press Z, okay, I think this might be the A button. Hold on. So I don't actually know which button is the A button. So what I'm gonna do is A. I don't know what the A button is. Trigger A button. What is this? Xbox controller. A button is number 1. Okay. So what that means is, again, in programming, numbers start at 0. So this right here is 0, and this right here is 1. Okay. So it's the X key. So when I go into teleop, let me bring up the logs. I'm in teleop now. I'm gonna press and hold the A button. Oh, oops. Oh, God. Okay. So you see here something. So in a command, what you can do is you can specify what should happen when the command is initialized. Okay, and this is called. So if you go over here, you see when I press the button, it says A button triggered this. Oh no, that's execute, sorry. Where is it? See initialize, when I press the button, this initialize is called. And then as I'm because this is on true, it'll never end. So you see here, it just keeps saying A button triggered this. What happens though is if I don't want this behavior, and the behavior that I want is when I let go of the button, it stops this command. So instead of on true, it's while true. Okay. And so what while true does, again, we will run the simulation again, is while the A button is held down, it'll run the command. But when I release my hand from the A button, then it'll stop. So if I go into teleop, watch this over here. Here are the logs, and I'm gonna press the A button. You see this? It stopped. When I press the A button, what happens is it says initialize, A button triggered this, and then as long as I'm holding down the button, it says execute. So this code is run. Okay. So that's the difference between on true and while true. Okay. So, hold on, I'm gonna pause it for a second. Okay, I'm back. So now, let's actually do something useful, right? This is just printing a command. But now inside of this command, now I can focus on the actual logic. Again, what is a command? A command is something that you actually want the robot to do, like move the elevator to a certain position or so on. And so now let's look at the structure of a command, okay? So for that, we're going to go over here to commands. Okay, so a command, by the way, what we're going to be doing right now is we're going to be going through the what a command actually is, like writing it out long form. And then what I'll show you over here is there's actually shortcuts. But first, if you just start with the shortcuts and you don't understand what a command can do, then you're not going to understand the shortcuts. Okay, so a command has a few different states where, or points in time where certain code will run. That's in the initialize, execute, and end method. So let me detail that out for you. Okay, so command life cycle. Okay, so what happens is initialize, I think that's right. Initialize, let's make this like that, no, like that. Okay, so there's initialize, there's the execute, okay, and there's the end. Okay, so what happens is when you first create the command, it runs, if there's an initialize method or code inside the initialize, then that'll run. And then, but that'll run only once. And then it goes to the execute. And what happens is, as long as the command is scheduled, it'll keep rerunning the execute every 20 milliseconds, 0.02 seconds, every 20 milliseconds, 002 maybe. The refresh rate is 50 hertz, which is 0.002 seconds, or 20 milliseconds. That I know, yeah. Okay, so every 20 milliseconds, the code in the execute is called. And so the idea, hopefully I'm not blocking it, good. Okay, so yeah, and so for example, the execute could potentially like, if you're driving, right? Your joystick is the joystick is constantly moving. So this execute, when it re-loops, it'll get the newest value of the joystick, and it'll like readjust the speed to the motor, for example. Okay, and then after that's done, after you the command is scheduled to end, this can be kind of like cleanup code. So for example, if you're shooting the note in this case, or shooting a ball, right? And this command, let's say, is shoot ball, initialize and execute, or maybe just execute, will ramp up the motor to a certain speed, but then the end will set the speed to 0. So that's what the end can be used for. Okay, so there's initialize, execute, and end. Now let's look at the command that we already, yeah, that's able to be read. So when I pressed the button for the first time, the initialize was run. And then actually, if you go over here, you see initialize a button triggered this, and then execute keeps being called, okay? And so that's kind of the anatomy of a command. So let's keep going. So initialization marks the command start. So it's called exactly once at the beginning. Okay. Then there's the execute, and then there's the end. And that's where you can put the actual code that'll do something, okay, in one of these three states. And then there's, let's see if we should go over it. Okay, so I'm not sure if we should go over it just now, but so there's an is finished method, which we should look into. Yeah, let's go over is finished. So for example, let's go back to Excalidraw, right? So we have initialize and we have execute, okay? But then so your robot doesn't really know if it should be ending the command or not. Like, how would it know? So what happens is, this is actually kind of a lie, but I mean, it's not a lie, it's just not fully complete. Okay. So maybe I can do something like that. So I'm going to make this is a function that's called so this is finished method. So this is how it is. It initializes, you can run code here. Execute, it'll run code here. Then after it runs the execute method, it calls an is finished function if it's defined. And then if this returns a Boolean, if it's not finished, then it goes and it reruns execute. If it is finished, oh, can you see? Yes, you can. If it is finished, then it'll stop the executing and it'll go to end. So that's what the is finished method is. Okay. So that's what the is finished method is, and that's about good. So get requirements is important, but we'll go over that later. And let's see. Yeah, so let's actually see it in action, okay? So, I mean, we see it in action right here. Okay, that was easy. Fine. So what should we do next? Now let's go over a subsystem, okay? So remember, going back to the diagram, we have over here trigger, command, and what we were doing in the command, in this print command, is we were just printing out a message. But in the actual robot code, the command is going to give orders to the subsystems to do something. Okay, so what we're going to do over here is, so I actually have a command that we created earlier. Let's go over it. Okay, so it has an initialize method. Okay, and we see that. So what is this doing? This is saying set drive motor to a certain speed. Well, the drive motor setting it to a speed. So what do we care about? We care about, we pass into the command a given speed that we want the motor to go to, okay? In this initialize, you'll see that what we're doing is we're telling, because the command doesn't know about the motor, the command has to ask the subsystem to do something on behalf of the motor. Wait. The command needs to tell the subsystem, it has to give it an order, in this case set speed. And then the subsystem will then take this speed and translate it to something that the motor knows about, okay? So that's kind of like the command is not going to the motor directly. It's going to the subsystem, and the subsystem will tell the motor what to do. And this is just so that you can, like, in one easy place, see what the subsystem, what functionality the subsystem has, okay? Instead of just saying, command, tell this motor on this port, this is what to do. It's like, you have to have that layer. You don't have to, but it's good to have this layer of abstraction. So let's go over what a subsystem is. A subsystem is actually pretty simple, and it's just a class of, well, sorry. A subsystem is nothing more than a piece of code which the main point of the subsystem is to declare hardware. Okay, so this subsystem is saying I'm responsible for a Talon FX, which is a Talon Falcon 500. The speed controller is called a Talon. Okay, and this subsystem is actually initializes the drive motor with a new Talon FX. And here's where you put in the port. This is kind of like the PID, the identifier for this Talon versus another Talon, okay? And so you'll see here, after we've defined this, we created a method called setSpeed. And if that should look familiar because that's what we expose to the outside world, or we expose to the commands if you want to set a speed, okay? So if you want to kind of like tell the drive motor what to do, okay? So we can create any method we want in here so that commands can then call those methods, okay? So now that we have this set drive motor to speed, I'm going to remove this, this print command because this is like nothing. And now let's actually make it so that the motor, so that when we press the B button, we'll make the motor drive at 50%, okay? So again, the trigger is B button, okay, equals drive controller dot B. Okay, so here's B button trigger. Okay, so that's what I've called it. And now we want to do B button trigger dot on true. And so so this on true again is right when I press a button, this should schedule a command. And the command that we want to schedule is set drive motor to speed. So what we have to pass in here is two parameters. Well, really there's one parameter, which is the speed that we want to set it to. So let's say 0.5. But we define the subsystems out here. In the robot container, we define all of the subsystems. And then if we look over here, this command needs access to the drive, right? It has to tell the drive subsystem what to do. So we pass it in as a second parameter. So if we go back over here, what we're going to do is we're going to pass in the subsystem as another parameter. And now everything should be working. So set drive motor to speed. Let's see. So this will work, but I don't know how this works with simulation. I mean, so this will work. So what I'm going to do here is because I'm in simulation and I don't have a robot, you can set up a simulation so the simulator will actually like show you the output of an actual motor. But for now, I'm just going to write a print statement, setting speed to this desired speed. Okay, so now let's run this. Or did I build it or did I simulate? No, simulate, good. Okie dokie. So what is this robot? What is this supposed to be doing? When we press the B button, we're going to set the drive motor to 0.5, okay? Or set this motor to 0.5. So, and right now it's not going to be commanding an actual motor. Oh, look, it has here. Oh, maybe it will work. Let's see. If I go over here and I uncomment this and refresh this, let's see if, let's go to simulate again. Let's see if it's actually going to run it, simulate the motor. It actually might by default. Let's see. Teleop, when I press the B button, yeah, cool, nice. So here you'll see, I don't know if you can see, but it set the duty cycle to 0.5. And that's what we want. But you'll see here that the motors is set to 50%, and you see down here, it's not going back to 0. Well, we should know why, because we've encountered this already. So what actually happens is we did on true, which means that it sets it to 50%, but it's never going to unschedule the command. Okay, so what we can do is we can do while true. And while true will, when you stop pressing the button, it's not true anymore. So it'll cancel the command. Okay, and you'll see that there's a slight issue here, but I want to take it one step at a time. Okay, so if you see over here the duty cycle, so in teleop, now when I press a button, it's going to go to 50%. And something's interesting is happening here. It says setting speed to 0.5, but it's not actually making it go back to 0. So let's fix that. So let's look at the command. And what happens when the command stops? We want to set it to 0. So what we want to do is, not is finished, but that's a good try. So public void end, we want to set it to 0. Initialize what? Hold on. End. We need to pass in Boolean is interrupted. We can go into that later. Okay, so that should work. Now when we simulate the robot, what will happen is as we're holding down the motor, as we're holding down the button, or while we're holding down the button, it will be 50%. But then when we let go, it goes back to 0. You see that? So 50%, and when I let go, it goes back to 0. And so this is how you would make, I guess, like a shooter. This is exactly it, right? This is a shooter because you want to set the drive motor to a given speed. Well, so it's actually kind of misleading because we're not actually telling it what speed to go to. We're telling it the duty cycle. And so now what we're going to get into is something that is Phoenix CTRE docs. We're actually going to go into how to control the motors. It might take me a second to find it. Device API. Okay, so Talon FX. So let's actually look into these. So there are two different types of control, motor controls. There's something called open loop and closed loop. Okay, open loop is saying, so how a motor actually works is, so the battery on our robot is a 12-volt battery. Okay, so if it's a 12-volt battery, and we basically run all of the voltage, all 12 volts through the motor, what it'll happen is it'll spin at its max speed, spin, let's say, forward. And then if you instead of positive 12 volts, you flip it, you make it so it's like 12 volts but the other direction, then it'll go full speed backwards. And the idea is that a duty cycle is a number between -1 and 1. Okay? -1 means full speed backwards. 0 means the motor should not be moving. And 1 means full speed forward. So when we're setting it to be 50% or 0.5, that means, so if it's 0 is off and 1 is full speed forward, 0.5 is 50% speed forward. This is what's called a duty cycle, okay? Duty cycle. So how do we actually use this duty cycle? So what you do is you create what's called a motor request, okay? It's called a request. So here, when I declared the Talon, I also declared this object, which is responsible for holding onto the duty cycle value, okay? So what I did is when the drive motor subsystem was created, I created this motor request as a duty cycle with its initial value as 0. So it should be off when the drive motor first starts up. Now this set speed, what it does is what you do is you call motor request. So the value of the motor request, if you go to motor request dot output, at this point, here, look, output. Well, it doesn't really like that. But proportion of supply voltage to apply in fractional units between -1 and 1. Right now, this output is 0. It's a double. It's 0 because that's how we initialized it. But we want to change that value. So instead of, to change this output, you call this with output command. Again, if you want to look at documentation, you can right-click and go to definition. What this does is it modifies the control request's output parameter and returns itself. Okay, so what it does here, you'll actually see it. What it does is it takes in the new output and overrides its internal output. So we just call this. And so now we have the control. Okay, sorry. So what we've done in here, maybe we can just split this out. You can split this out like that, and then call motor request. This does the same thing. So what this call does is it sets this output, which was originally 0, to the new value. Okay, so that's that, right? We're taking it one step at a time. You can also, instead of saying go, as a fractional unit, -1 to 1, you could command the motor to be supplied, let's say, 8 volts, right? You can specify the actual number. Again, the issue with specifying a voltage directly is that, yeah. Oh, this control more stable and reproducible behavior. Ah, I see. Okay, this is interesting. So when you fully charge a battery, it's a 12 volt battery, but if you fully charge it, it's around 13 volts. Okay. So if it's around 13 volts, then then a duty cycle of 1 will pass 13 volts through the motor. However, if you have a duty cycle of 1, right, full speed forward, at the beginning of the match, the motor will be spinning super fast, but then by the end of the match, as the power drains in the battery, you're going to have less voltage. So the 100% forward is actually going to be slower, which is why instead of specifying the duty cycle, you can also specify the voltage. And the idea is that if you pass 8 volts through the motor, then the motor will go at a certain speed, let's say 1,000 RPM. But then that's consistent throughout the course of a match. So, for example, for a shooter, it's good to use the voltage command directly. Well, kind of. Um, Because here, this says, since the output of the voltage control request is unaffected by the supply voltage or the voltage of the battery, this control output type results in a more stable and reproducible behavior than the duty cycle. So this is unaffected by what the maximum voltage is in the battery, okay? And then this right here is, we're gonna skip this for now. Okay. So that is, these are what's called, okay, so let's go to open loop control. So open loop control is where you're setting the value, setting the, this is not really a speed, right? A speed is measured in like revolutions per minute or RPM or how fast it's going, right? What we're doing here actually is we're really just setting the motor request as a duty cycle. We're setting the duty cycle. Okay, if you're setting the duty cycle directly, you can't, there's not really this feedback loop which will say, oh, this duty cycle is going to make the shooter move at 1,000 RPM. So that's the difference between open loop and closed loop control. Open loop is it's like set it and forget it. You're saying set it at 100% speed, and I don't care what the actual speed is, just it's going as fast as possible. So for example, when you're driving around in teleop mode, this is open loop control. If I make the joystick go at a fully forward, I want you to make the motor spin fully forward, okay? Cool. And this is how you do it. So so this is a tank drive or one implementation of tank drive. Look at what they do. They create the motor. They're calling the left and right motors, okay, on ports 0 and 1. They're setting the duties, they're controlling it via the duty cycle. Again, that's a number from -1 to 1. Here, they're getting the values of the joystick. So forward is going to be controlled by the left Y axis. So the left joystick and then the Y axis up and down. And the turning is going to be the right joystick and then the X axis on the right joystick. Here they're doing the calculation, and here is where they're setting control. This is exactly what we're doing over here. Exactly the same. So let's see if we should now what we should do. Should we go over closed loop control or should we go through, okay, so we are going to, I'll give a very basic understanding of closed loop control. We're not going to go into the details right now, but just so you, or maybe we will, I don't know. Okay, fine, we will. Because we're on the topic of open loop, it would be silly to not go over what closed loop is and like say, oh, we'll do it later. Let's do it now. Yeah, let's do it now, fine. So closed loop control. So as I said, open loop control is set it and forget it, right? What we're doing is we're telling the motor how powerful it should be, you know? But for a lot of different mechanisms, we don't actually care about what control we're sending to the motor. What we care about is that the motor is whatever you send, whatever voltage you actually send to the motor, it's kind of in response to what we want to do or what we want the mechanism to do. So if we go back to Excalidraw and we go into the commands here, okay? Elevator to high position. For example, if your elevator is like this, right? Here's your elevator. And this elevator goes up and down, okay? Up and down. So there's a motor which says, okay, make this second stage go up and down, okay? So a question is the following. If let's group these together. Okay, so this, let's say, when you want to move the elevator to the high position, let's say what that means is this dot should go over here, right, in line with this high position. If the stage is right here, you would think that because this point is, or the bottom of the elevator is so far away from the set point, you want to set the control relatively high. Sorry, set the motor to go with a high speed. Okay, but if you're over here, you don't want the motor to go super fast. You want it to slow down, right? Because if it reaches here and it's like set to 1, right, full speed, then it'll take some time to stop. And if it doesn't have enough time to stop, the elevator can break itself. It can go and break, and then you're sad. So this is what's known as closed loop control. One more example, PID control. Images here. So we're not going to, as I said, we're not going to go too much into it right this second, but this blue right here is, let's say, what you actually want. What you actually want is, let's say, this point to go right here, okay? So right now, it's super far away. So you're going to have the motor go super fast, right? But then as you get closer, you'll see that the slope of this line, which tracks its position, starts to slow down, okay? And so this is called control, closed loop control, okay? That's where I'm going to stop on the depth of what closed loop control is. But let's actually now just read this. Closed loop control refers to control of a motor that relies on sensor data to adjust based on error. Mechanisms that rely on maintaining a certain position or velocity achieve this through closed loop control. This is achieved by feedback, or PID, and feed-forward control. Feedback, I'm sure if we go here, is, do they have a picture? Right here. So here's the feedback, and here's some more information on what a PID controller is. Okay, we're not going to get into it right now. And then feed forward control. Do I want to go into it? Let's see if there's, no. We're not going to go into it right now. Closed loop control can be performed on the robot controller or on the motor controllers themselves. So either what you can do is inside of, for example, inside of your command, you can create a PID controller here. So you can, in your command, you can actually have the PID controller, okay? Or what's really cool though, is you can have the actual Talon FX motor controller do that for you. And you can tell the Talon FX, like what are the PID like parameters, which are numbers. And then what you can do is you can tell, instead of saying set control to a duty cycle, you can tell the motor controller, go to this position or go to this velocity, and it will figure out, it'll do this like PID calculation to figure out what the desired speed should be. The benefits of onboard closed loop control are that there's no latency and the closed loop controller has a 1 kilohertz update frequency. Basically, this means that here you have, here you have your robot, okay, and, here you have the Talon. Okay, so you can have, and here, this is the PID controller. So you can have the PID controller operating on the robot, which means, you know, in this command itself. Or you can have the Talon do its own PID calculations. And it's always, I think always, much better to have the Talon run the PID for you. It's much faster. Let's just put it at that. And it updates much quicker, so it's great. Since closed loop control changes based on the dynamics of the system, closed loop relies on PID and feed forward parameters. Okay, so basically, right, for example, a shooter, you can think of if the shooter, the flywheel, the actual wheel that spins, if it's very heavy, then it's going to take longer for the system to get up to a certain speed. But if it's light, then it'll go much quicker. So that will change the parameters that you need for closed loop control. So that's what that means. And the parameters, the question is, how can you find it, right? It's like, how do you know what the P value should be, the I value should be, the D value should be? There's two ways of doing it. The first way, I think, is an automated way, which tuner configs, hold on. No, it's not here. Okay, the parameters can be determined using, it's called sysid. Sysid, which I've never done, but they have they have a way, I think actually in here, no, wpi-lib start tool sysid. So you can open what's called the sysid, and what it will do is, I've never done it, so I can't really give the actual like instructions. on how to do it. But what it'll do is it'll actually run the system. So what you do is you like connect to the robot or something. Maybe let's actually see what the documentation says. So what you do is you connect to the robot. And what you do is you tell it what kind of mechanism is it. Is it a shooter? Is it a drivetrain or so on? I think shooter is just general. And what it'll do is you give it the motors that are running the system, like let's say the shooter, and what's the feedback or the encoder, which is tracking what the, the speed of the shooter is, for example. And you do a bunch of these things, and gearing if there's any gearing. And then you deploy the project. Yeah, you connect to the robot. And what it'll do is it'll run the tests. It'll run a few different types of tests, and it'll generate plots here. And it's kind of like in math or in your math class where you do like best fit lines. What it'll do is it'll collect sensor data and then try to fit a curve to the data that it collects. And from there, it finds out what the ideal parameters are. In this case, it's KV and KA, I guess. Okay, so basically all this is doing is it's an automated way to actually experimentally find out what the right values are. And so this is what calibrating the drivetrain looks like. So this is the test running. So it runs this test and it's collecting sensor data. Okay. I think it does that and then it goes full forward or something like that. Oh, no, it goes forwards, backwards, and it's collecting data. And then it goes forward fast and backwards fast, I think. Yeah. Okay, once we have an identification routine, we can analyze it. So you can analyze and see here are the sensor data points that it collected. And what it does is it finds the best P, D. So this right here is velocity. So it'll give you the right P and D values to basically best control this this mechanism. So we can go over it once it's more relevant. So you see here, it like found the best fit line, and then therefore and then you can plug that data into the code. Okay, that was, and then what you can do is go all the way down here. How do you actually use it? So so what you do here, this is the code that you write. All of that was to get these magic numbers, P, I, and D, okay? And then what you can do is you can configure the Talon with these P, I, and D values. And then what's very cool is instead of saying, I want it to go at 50% speed, you can say, I want it to go 10 rotations. And then it'll figure out how to get to 10 rotations, which is very cool. Also, so this, I see. So look, position control, if you want to control the position, let's say on the arm or on an arm that's going up and down, or if you want to control an elevator, this is position control. And for that, you need P, I, and D. Okay? But if you want to control the velocity, how fast something is spinning, you need P, I, and D, and then two other values, S and V, which are all determined from that test. Okay? And then you can just say, I want the Talon to go at 8 RPM or RPS or whatever. Okay, so that's very cool. So let's stop there. I apologize that it might have been a little bit confusing. I have 20 minutes left, so now let's go over okay. So now we're recentering and focusing on a new topic. And that topic is let's start to create the infrastructure for a Swerve drive system. FRC Swerve. Swerve drive looks like this. And let me go to a YouTube video. Swerve drive video. And what a swerve drive is it allows your robot to move in any direction without having to turn. So it can turn and move independently. What actually is, and then you can get these cool effects, like these cool driving patterns. What you see is there's 4 independent wheels that can turn and drive and spin the wheel, okay? So on each of these modules, there's actually 3 different electronic components. There's 2 motors, one to control the turning, one to control the speed of the wheel, and then there's an encoder which gets the value of the which reads the what angle the wheel is at. Okay, so Scala draw. So now let's turn our attention to, let's say this is the robot, and there's 4 wheels here. Okay. So inside, so this right here is called the Swerve drive, the Swerve subsystem or drive subsystem. And this right here is the module, okay? So if you think about it, a module has 2 motors and 1 encoder, okay? And the Swerve has 4 of these modules like that, okay? So what we're gonna do is we are gonna we're gonna create the module, and then we're gonna create the Swerve subsystem. Because once you create the module, then you don't actually have to worry about the motors and encoder, because the module knows about that. So the Swerve subsystem just says I have 4 modules and I can set these modules to whatever I want. Okay, so let's figure out how to create a module, okay? So what I do to create a module is I'm going to create a module class, okay? Again, there's, here is, I can declare the hardware. This is the constructor and methods. Okay, so the constructor is, and this is kind of a recap for those newcomers. Basically, a constructor is a very special function which whenever you do this new keyword, when you first create the object, if there is a constructor defined, this code is run initially. So the constructor, how you can say that this is the constructor, is it's called, you do public, and then it's the name of the module here, or it's the name of the class. So in this case, it's module. So what's important with subsystems, the constructor is usually where you initialize the hardware. So what is a module created from? What does it know about? It knows about 2 motors and an encoder. Okay, so the motors that it knows about is let's say, first of all, it's going to have a Talon FX for the drive, and it's going to have Talon FX for the turning or steering. Let's call this turn. Okay, so it's going to have two talons that it knows about. And so now this module, we're going to pass in the ports, right? Because the identification for the drive motor. And then what we're going to do is we're going to initialize the hardware. And I'm having Copilot write it for me, which is cool. And so here, what I've done is I can just say the drive motor right here is, and I'm creating it, the Talon with the new keyword. Okay, so now this module knows about this drive motor and turn motor. It also needs to know about the encoder, and for this we're using it's called a CAN coder. Where is it? Import. Hardware dot import CAN coder. Nope, I don't know where that is. So what I'm gonna do is I'm gonna do Phoenix 6 CTRE documentation, and let's look for the CAN coder. Device API, Talon, no. CAN coder, let's see how we program this thing. FRC CAN coder code. Okay, so it's in import that. Does that work? Phoenix 6 dot no, where is it? You know what I'm gonna do? Let's do this swerve mechanism, and then I'm going to see. Dot, here you can see everything. Here we go. So we got something. Utility dot. Let's look. This is version 5. Okay, so that's not what we want. CAN coder. Let's look at other code that uses that initializes the CAN coder. Let's do this. Can coder equals new can coder. Where is this from? What? I thought I did that. Okay. Okay. What? I don't have. What? Can't. Okay, fine. So can coder. I'm not sure what happened. Very strange. Okay, this is super strange. I'm not sure why that happened, but fine. So I can create a can coder there. So here I created the turn encoder, and here int can coder port. Okay, so here's now my can coder port. Now let's do one more thing. Okay, we're not going to get to all of this right now. I have 9 more minutes. So now what we need to do is, just as in this drive motor subsystem, we have the set speed function. What we want to do is we want to allow the module to expose a function called set, kind of like set speed, okay? But we actually, okay, so that's kind of cool. But what we're actually doing is set module state. So there's something called I think it's in edu WPI, no, first dot drive, let's see, dot differential mecanum robot, no, maybe 2. I don't know what I'm looking for. WPI lib swerve module state. Swerve drive kinematics. Here. Okay. Oops. Current state is equal to. Okay, so instead of saying, okay, what I want the speed to be, we can say, because what we really care about setting the module to is 2 different values: what the speed of the motor should be, what the angle should be of the module. So what we want to do is that's all inside of this swerve module state here. Okay. So how this works is, what it does internally, it has 2 different internal parameters. One is the speed in meters per second, and the other is the angle of the module. Okay. So this Swerve module state by default is set to, okay, fine. So what we want to do is, when we set module state, the Swerve subsystem should be able to give the module a state that it wants the module to go to. Then it's the module's responsibility for getting to that state. So what we can do is Swerve module state, desired state. Okay, this is getting a little complicated. So what you're gonna do is current state and like desired state. Okay, so what you can do is desired state, and this could be target state. Yeah, this is getting a little complicated. But basically what this is doing is it's saying, okay, here is where I'm at currently, and here's where a target state should be. And then there's gonna be a method which says, well, is my current state different than my target state? If they're the same, then I don't have to do anything. But if they're different, then I need to drive the current state into the target state. So if the target state is saying I want to go move the drive train faster or move the wheel faster, then this will tell the drive motor go faster. And but if the current state is faster than the target state, then it'll say, okay, slow down. And so that's how it kind of works. So now you just have to have an execute method, or not a periodic method that that drives the current state to the target state. So I guess we'll end here because it's a little complicated and I don't know how to teach it so well. Peace.